Today I'll be covering a bit about the wolfSSL compatibility layer and going over migrating projects from OpenSSL to wolfSSL. Going over the four main topics of what is the wolfSSL compatibility layer, building the wolfSSL compatibility layer, and a simple example application demonstrating its use, and finally examples of major projects that the feature has been used in. The wolfSSL compatibility layer provides a means for making calls to OpenSSL API functions, but with having the wolfSSL native implementations be used instead. With the use of macros, it maps a subset of OpenSSL APIs down to wolfSSL's native APIs. The compatibility layer is constantly getting expanded as new projects get completed, and there's currently more than 400 of the most commonly used OpenSSL APIs supported. In addition to mapping functions, there's also support for a subset of structures and common enums. An example of a few of the crypto APIs supported would be implementations for things such as the EVP and bio functions. Covering a bit more about the crypto API supported, there is support for EVP init, update, and final function calls. In addition to the init, update, and final function calls, there is signing and verifying EVP API available. These EVP functions mentioned are abstracted functions that OpenSSL uses for many different underlying algorithms, such as performing an RSA signature operation or doing an AES encryption. There's additionally support for direct calls to hashing algorithms, like calls to the function SHA and SHA-256, along with support for direct calls to AES encryption and decryption functions. The peak key structures are supported to help with using the crypto and X509 API mapped to by the compatibility layer. This allows for loading in and working with keys using an unaltered application that was previously linked to OpenSSL. The problem that the compatibility layer solves with having all these APIs and structures mapped is to allow for easily migrating from OpenSSL to wolfSSL. This is with having an unaltered application that was previously linked to OpenSSL and migrating it to wolfSSL by only updating the library that it's linked to and the include paths. Here's a brief snapshot of the main header for the wolfSSL compatibility layer. It shows places where the names of OpenSSL structures get mapped to wolfSSL implementations, such as with the EVP peak key and the bio structure. It also shows a couple of the main TLS API mappings, such as the SSL new and SSL CTX new functions. The bulk of the code mapping APIs will be located in this SSL.h file. Before getting into the example application and how to build wolfSSL for use with the compatibility layer, I'd like to cover why someone would want to turn on the compatibility layer feature and why they may want to migrate from OpenSSL to wolfSSL. There are many reasons for wanting to make this migration. I've listed out some of them on this slide. One reason is that there is a lot of hardware acceleration ports that wolfSSL offers, from the usual ARM assembly or Intel AES-NI all the way down to embedded uses like with the Freescale MMCAU. Another point of interest to many is the addition of progressive algorithms and the early adoption of TLS 1.3. With the reduced footprint size of wolfSSL, users are able to reduce the number of resources dedicated to TLS connections. Later on with the example, I will show just how much the heap size can be reduced by migrating to wolfSSL. A couple other reasons for the migration may be for the FIPS code offered by wolfSSL, to get support from engineers who work with and wrote the code, or because of the clear licensing model offered when using it in projects. That covers the basics for what the wolfSSL compatibility layer is. Next is going through the steps of turning on the feature when building the library. To build with the compatibility layer enabled, when using auto tools, the flag enable OpenSSL extra can be used. In addition to the OpenSSL extra flag, there's also OpenSSL all flag. OpenSSL all enables a superset of implemented functions by including some of the API implemented when expanding the compatibility layer for use with open source projects. If building in an IDE or cases where AutoTools is not being used, then the macro OpenSSL_extra can be defined. This macro can either be passed as a preprocessor flag or, better yet, set in a user settings.h file. When linking against the wolfSSL library and having built using AutoTools, the file wolfSSL options.h should be included first before any other headers that are used from wolfSSL. This is to make sure that the application is using the same settings as what the library was built with. All header files needed for migrating an application over to wolfSSL are located in the directory wolfSSL OpenSSL. An example of that is the SSL header file listed at the bottom of the slide. With the internal behavior of wolfSSL being different than OpenSSL, there is some cases where only subfunctions were needed in projects. These are functions that allowed for compiling the code but do not actually do anything when called. It is also the case that when migrating some projects over to wolfSSL, the features were not needed, so the functions were not finished at that time. It can be useful to tell whether your application is calling a stub function or not, and to help with that, either the debug feature can be turned on with enable debug, or the macro no wolfSSL stub can be defined. Turning on debugging prints out a warning message each time a stub function is called, and defining the no wolfSSL stub macro will throw compile time errors if the application is attempting to use any stub functions. wolfSSL is a very modular library in how it can be built and configured. With this being the case, additional features such as key generation would also need to be turned on at a compile time if wanted. In addition to that, most hardware acceleration implementations that we have would also need to be turned on at compile time if wanting to be used. That covers the basics for how to build the wolfSSL library in preparation for the Great Migration. The next items are covering how to use the library once built, and example cases of projects that the feature has been used with. When migrating an application from OpenSSL to wolfSSL, one of the things that needs to be resolved is including the right header files. OpenSSL headers should no longer be used, and the header files located in wolfSSL should be used instead. This is typically achieved in one of two ways. Either with changing the preprocessor include path to point to the wolfSSL directory with the OpenSSL compatibility header files, or by changing the application code to have wolfSSL prepended to the includes. In most projects, we opt for the first option because it does not require any code changes to the application and is done by simply adding a preprocessor flag when compiling. The next thing that needs updated when migrating a project over is the library that it is linking to. When an application is linked against OpenSSL, the library SSL and crypto are used. This should be changed to be wolfSSL so that the application is now linking against the wolfSSL library instead of OpenSSL. The migration is complete after building wolfSSL, setting the include path, and updating the library link to. It's as simple as that. Here are two examples of altering the include path and library link to. The source file, the Great Migration, is a simple TLS server written for this demonstration that uses OpenSSL's APIs. The first example command line executed has the application using OpenSSL headers and linking to the OpenSSL library. The second line executed shows updating the include path to point to the directory where wolfSSL headers are. In addition to adding the include path, I also used the -include flag, which tells the compiler to include wolfSSL options.h as the first include file when compiling any source code. And finally, to have the application linked to the wolfSSL library created, the links to SSL and crypto were changed to wolfSSL. From executing each of these commands, a open.out executable was produced when linked to the OpenSSL library, and a wolf.out was produced when linking to wolfSSL. This slide shows a small code snippet of the example TLS server used. It shows the bulk of the TLS code after a certificate has already been loaded and a client has initiated the TCP connect. In the code, only OpenSSL API was used, which when using the wolfSSL compatibility layer gets mapped to wolfSSL native API. You can see the typical OpenSSL API calls such as the SSL set FD, SSL new, and the read and write TLS functions. This slide highlights the difference in heap used with default builds for each of the libraries. To collect the heap usage, I built the application on Ubuntu 16.04 and used Valgrind's massif tool. Then to make the pretty graphs for this display, I used massif-visualization. In both cases, the cipher suite used was ECDHE, RSA, AES-256 GCM with SHA-384, and the same client was used to connect to both servers. With using OpenSSL version 1.0.2g, the peak heap used during the connection was 101.3 kilobytes. In contrast, when linked against wolfSSL version 3.15.3, the peak heap used was 35.7 kilobytes. Each of these examples was with default builds. wolfSSL also has some optimizations that can be set for reducing the amount of resources even more. Getting a heap size usage for the same cipher suite down to around 22 kilobytes. Using a third of the heap and possibly even less after optimizations leads to freeing up resources for other uses than TLS. That covers an example of using the compatibility layer and resource use reductions. The final item to cover is examples of major projects used in and determining if all APIs needed for migration of your project are available. This is a list of some of the major projects that the compatibility layer has been used in. It's been used in Lighty, S-Tunnel, OpenSSH, Nginx, MySQL, HA proxy, curl, and many more than what we have listed here. For many of the major open source projects that we port to with the compatibility layer, there is an associated enable option. This is to guarantee that all features used by the open source project are enabled when wolfSSL is compiled. An example of this would be the enable Nginx or enable HA proxy. And this circles back to the modularity of wolfSSL. Maybe if like using Nginx, for example, or some other open source project, and we needed that keygen enabled, the enable Nginx would take care of enabling keygen features. The full changes done for Nginx can be found on wolfSSL GitHub repository. With the compatibility layer being a subset of all possible OpenSSL API, there is a chance that some API used in your application may not yet be implemented. The easiest way to tell if there's some missing gaps in implemented API is to compile the application with linking against wolfSSL. This will list out compile time errors for all unimplemented functions. If it is found that any API are missing, we do accept feature requests or offer consulting for expanding the compatibility layer as needed for the project. That gives a summary of what the wolfSSL compatibility layer is, why it would be used, and example cases. At this time, we're going to go ahead and open up the floor for questions.
We have a question. When should the wolfSSL command utility be used as opposed to the direct API calls?
The compatibility layer is typical, or is this the command line utility? I guess I should distinguish whether it's the compatibility layer or the command line utility we're talking about.
I think it's CLU, so command line utility.
Okay.
I'm guessing, but let's see. Yeah, command line.
Okay. Command line utility is basically just for ease of use. It's similar to like the OpenSSL command line utility. So we would use that instead of native. Well, it does call down to native wolfSSL API when using the command line utility, but it's to help with things like generating keys or changing certificate types from PEM to DIR. It's just to make those type of operations easier by executing them from the command line utility.
Okay, thank you. Okay, can OpenSSL and wolfSSL be linked at the same time, or does it have to be one or the other?
It has to be one or the other when the compatibility layer is enabled. The only way that you could link to both at the same time is if the compatibility layer was turned off and the application was using the native wolfSSL API.
Okay, thanks. And another question here, and feel free to enter your questions in the Q&A box or raise your hand and I will unmute you, just as a reminder. Is there specific versions of OpenSSL supported?
For some projects, there has been a requirement that a specific OpenSSL version be used, but the compatibility layer as a whole isn't specific to any one OpenSSL version. It can be used with a broad range of OpenSSL versions and isn't limited to just one.
Thank you. Okay, next question. How does performance compare with OpenSSL versus wolfSSL?
Okay, so we saw the resource use. That's a great question. We saw the resource usage difference, but as far as like performance and speed, wolfSSL has recently had quite a few modifications and speedups done to it. We have a benchmark page on our wolfSSL.com website that shows that many of the common algorithms are on par with OpenSSL, or in some cases even faster.
Great, thank you. Are there any other questions? Just give it a minute to see if any other questions come up. And just remember, following the webinar, if you do have any questions, feel free to email us at info@wolfSSL.com, or you can respond to the webinar invite as well. Following the presentation, I will send out a link to the recorded webinar, and just let us know if there's anything, if you have any other questions, or if there's anything else that we can help you with. Well, Jacob, I don't see any other questions, so it looks like we're finishing up a little bit early today. Thank you, everyone, for joining. Jacob, thanks so much for the presentation. Useful information. And if there aren't any other questions, we'll go ahead and end the webinar. Thanks so much.